Hi friends, I'd like to find support reaction for a cantilever beam. So we shall take an example of a cantilever beam. So here we have got a cantilever beam. So the free end of the beam is point A and the fixed end of the beam is point B. And here overall span of the beam from here to here is 4 meters. There is a load of 100 Newton acting at the free end, and there is a uniformly distributed load of load intensity 50 newtons per meter is acting from point C to point B. So in this particular case we have to find the support reaction at point B, because there is a single fixed support at point B, so we want to find the support reaction at point B. In case of cantilever beam, there will be a force reaction acting at support point B. So let's say that the support reaction acting at point B, which is a force reaction, is a reaction B, that is RB. And there shall be also a moment reaction acting at point B. So this is the moment reaction which is acting at point B. This I am going to call as MB, that is moment reaction at point B. Okay, so we have got the forces acting on the cantilever beam. Point A is a free end of the beam, while point B is the fixed end of the beam. And there is a uniformly distributed load acting between point C and B. So distance of point C to point B is also given to us. So this distance is given to us, that is 2 meters from here to here. So we have got the complete condition. We have got the condition of a cantilever beam. Also there is a support reaction in terms of force is RB. There is a support reaction in terms of moment is MB acting at fixed end, that is point B. Now we have to calculate the support reaction, that is RB and MB acting at point B. So we shall be using the condition of static equilibrium. This is a uniformly distributed load. So in order to calculate the support reaction, we have to convert this uniformly distributed load into a point load. So for that, what we will do is we will multiply the intensity of load with the length over which it is acting. So 50 Newton per meter is the intensity. It is acting over the length of 2 meters. So the overall point load will be 50 Newton per meter multiplied by the length over which it is acting, that is 2 meters. So this meter get cancelled out. So 50 into 200. So the point load equivalent value is 100 newtons. Okay, it is going to act at midpoint of the length on which uniformly distributed load is acting. So I can say it is acting at the midpoint somewhere here like that, and the value is 100. It is just for reference I am writing 100 Newton, and it is acting at distance 1 meter from the fixed end, we can say like that. Okay, so if you wanted to show that, you can show that this distance is going to be 1 meter. So now for the calculation we shall be using only this 100 Newton, because this 50 newtons per meter is converted into the point load, okay, and which is acting at 1 meter from the point B. So for our calculation now we shall be using only this 100 newtons. Okay, so now we'll start the calculation. So it is based on condition of static equilibrium. So by condition of static equilibrium, so we know that according to this condition, summation of forces in the vertical direction will be 0, summation of forces in the horizontal direction, that is Fx, is equal to 0, and summation of moment, you can take any point, whatever you would like to do. I shall be considering point B. So summation of moment about any point is also going to be 0. So these are the condition of static equilibrium. Now in this particular case there are no horizontal forces, so we can avoid this particular situation. So we can only take summation of vertical forces, that is summation of forces in the y direction is 0, and the summation of moment of forces about any point, you can take point B, is going to be 0. So I'll first start with this condition. Therefore by summation of forces in y direction equal to 0, you shall be getting, so what I will do is all the upward forces I shall be considering positive, and the downward I am going to take negative. So this 100 Newton is acting downward, going to be minus 100 Newton. There is a point load we got, which is equivalent of the uniformly distributed load, so it is again 100 downward, so minus 100 again, and then there is RB upward, so plus RB is going to be 0. So if you further simplify this equation, So you will get RB as 200 newtons. So this you can call as equation 1 for our reference. Okay. Now it is very clear that all the upward forces must be equal to all downward forces, because the beam is balanced in the vertical direction. So downward force is 100 over here, 100 over here. So 200 must be equal to RB. Okay. Now the next part what you would like to find is the support moment reaction, that is MB. So we'll take the second condition over here, summation of moment about any point equal to 0. So that is point B I am going to take. So by condition summation of moment of forces about point B, okay, must be equal to 0. So what you will get from here, let's see. So if you hold the beam at point B and hinge it, so beam is hinged at this particular point B. Okay. So now due to application of this 100 Newton, the beam is going to rotate in the counterclockwise direction. So there is a rotation about point B. So 100 into distance 4 meter. So I am going to consider sign convention, and sign convention is very simple. The clockwise I am going to take positive, and anti-clockwise I am going to take negative. So it means if your beam is rotating clockwise, I am going to take moment positive, and if beam is rotating in the anti-clockwise direction, I am going to consider it as a negative. Okay, so let's see how the beam is rotating in this case. So when it is hinged at point B and 100 Newton load is applied, your beam is going to rotate in this fashion, which is anti-clockwise direction. So anti-clockwise will be negative, friends. So I'll write down minus 100 into 4 meters, because the distance between the force and the point about which it is rotating is 4 meters on the entire span length. So 100 into 4 meters, right? Similarly, due to 100 Newton this point load, we can say it is going to rotate again anti-clockwise, and distance is 1 meter. So again minus. So now due to 100 Newtons force, the beam is going to again rotate in the anti-clockwise direction. So it is 100 into 1 meter, but minus. Okay. Now next, at point B there is another moment acting, which is MB. That also you have to consider, but this moment is going to rotate the beam in the clockwise direction, because this moment is clockwise. Okay. Why it is clockwise? Because it is preventing the entire beam from tilting or from rotating in the anti-clockwise. So this is a clockwise moment. Always the reaction will be trying to prevent the rotation of the beam. So in order to prevent the rotation of the beam, your reaction moment has to be in the clockwise sense, because this beam has natural tendency to rotate in the anti-clockwise direction. Okay. So this has to be understood at this particular level. So this is going to be clockwise. So I am going to write plus MB, and that is going to be 0. This is very simple, friends. Now from here what we can do is we can simplify this entire equation. So you will get 100 into 4 400, minus 100 into 1 100. So minus 400 minus 100 is going to be minus 500 plus MB equal to 0. And then if you simplify this, friends, it is going to be MB equal to 500. Please remember, the unit of moment is going to be, the unit of force is Newton and distance is 1 meter, so it is going to be Newton meter. Okay, so this way we got support force reaction RB as 200 Newton and support moment reaction MB as 500 Newton meter. So by this procedure you can easily find out the support force reaction, which is RB, and support moment reaction, which is MB. Okay, so similar procedure you can adopt to find out the support reaction of a cantilever beam. Thank you very much.